Have I done what?
Have you made any projects like this for your personal?
No, this is more involved, right? This is heavy engineering. A lot of engineering. You need a team here. I mean, not just a small team, but like lots of people. There are some graduate students who are looking into small problems related to this, like highway merge, just merging into a highway.
Graduates?
Yeah, not in a university. Yeah, I mean PhD students. Are you done? Okay, so just waiting for you. So for those who came late, try to fill in the course evaluation forms that were sent to you. Okay, so we haven't yet started actually. So okay. Sorry, I was just showing a video of I think this came around last week, and I'm going to show the video again maybe after a break or something. So it was about Tesla's self-driving car. I mean, doing a transportation from, I guess, A to B, point A to point B, in a really nice. I mean, it's, I guess, a next good PR video. So it has some bearings. I mean, some underlying technology has some relation to what we're going to study today. So that's why that video. Anyway, so today we're going to cover the following aspects. And so at the end of the lecture, you should understand what reinforcement learning is. What are the key concepts or key blocks in this particular type of problem. Okay, it's slightly different from supervised learning. Just like in supervised learning, you know exactly what's the model, what's the feature, what's the labels, is it continuous or is it discrete. You know a lot of things about supervised learning. Similarly, for reinforcement learning, you just need to understand at least the basic building blocks. Okay, may not be, because it's only one lecture today, but and maybe we're also going to discuss reinforcement learning again next lecture. But you need to understand what the basic building blocks are, and for that, one of the building blocks is called a Markov decision process. Okay, it's a way of viewing things, just like maximum likelihood estimation or probabilistic graphical models are a way to view at unsupervised learning problems or supervised learning problems. So there's this object called Markov decision process that lets you define or lets you talk very concretely about what are you trying to build. Okay, what's the goal, right? What's the goal in English is kind of easy to say, but what's the goal in terms of like very concretely as a expression is what you'll get as one of byproducts here. Next, once we understand Markov decision process, there's going to be some things involved with the MDP, I guess, definition that you can derive from an MDP or a Markov decision process. One is policy. Okay, what's a policy? What's values? There are going to be values for something called states or contexts. Okay, so we're going to kind of understand those two, and then we'll also discuss what is called Bellman expectation equation or Bellman optimality equation. They're just names for some equations that kind of are important in these Markov systems. Okay, Markov systems just mean they just only depend on the previous situation. Okay, they don't depend on the entire history of the world, history of your environment. Okay, so we'll see how these. I guess in the fourth bullet point is all about how these equations can let us think of algorithms. Okay, the algorithms will try to learn something. In fact, they'll try to learn policies. And so we'll see how the last bullet point, they'll help us think about some intuitive algorithms. Okay, and one well-known algorithm there is called Q learning. Okay, so Q learning is what we'll end today, and then next time we'll look at more advanced versions of Q learning, which have appeared in the past 5-6 years. Okay, any questions about the goals? Okay, let's go to. Oh, okay. Which one is it? Okay. So this is the outline for today. We're going to first, just revisit complex decisions or decisions which are non-trivial. Okay, that's all I mean. There's nothing technical here. And then we're going to look at the basics, like the Markov decision object that I was talking about, Markov decision process object that I was talking about, and then what is called values or value functions. Okay, and then finally we'll cap it off with Q learning algorithm. Okay, So what's q here we'll figure out midway. Okay, it's essentially a name for value function. So basically, if you just knew supervised learning and you did not take a lecture on reinforcement learning, how would you kind of mix learning and decision making, right? So you would potentially, there are many ways, but one way would be the following, right? You build a really good forecasting model, minimize mean square error or some sort of accuracy metric or something like that. Given your batch data just means you have offline data. Okay, build a really good forecasting model. It's essentially linear model or a neural network. And then once you have the model, okay, maybe on current test instance, you may have one test instance or multiple test instances. You use those test instances to make some forecasts. Okay, maybe one forecast or several of them, and then maybe that one number or several of those numbers, you'll plug it into an optimization problem. Okay, and you have seen several optimization problems in this course, and some of you have done revenue management or some logistics course or something like that. So you know what an optimization problem looks like. There's some objectives, some constraints, and there's some variables that need to be fixed or searched over to get to maxima or minima of the objective, right? These forecast numbers will be data of that optimization problem, things that won't change. Okay, there are only two parts in the optimization problem: addition variables and then data. Okay, so these forecasting numbers will be data, and then you take a good decision based on forecasts and constraints of your system, maybe inventory decisions, and then you just take those apply those decisions in real world. Okay, so that's one way to just take complex decisions from after learning from batch data, after doing supervised learning, right? Is that workflow kind of clear? There's no confusion there, right? Any confusion? Okay, so that workflow is fine, but that's just one step. You're taking a one-shot decision actually. So you're doing a batch learning, which means that given offline data, you're just learning a forecasting model, and then you're taking one-shot decisions, and then you're not really doing anything more than that. That's like one step. Okay, now this whole business of reinforcement learning, as well as the content of last time, is about doing this forecasting and decision making in a for loop. Okay, so you forecast, make some decision, you also get some information about how good the decision was, whether the decision was really good. Okay, you made tons of sales, made a lot of money, or you had a lot of leftover inventory, or you kind of made a loss. Okay, so that given that feedback, okay, that feedback is essentially like a new data point. Okay, so for that's going to be a new data point. That's not going to be may not be in the form of x comma y pair, but there's some information about how good your decision was, right? So based on that information, you will have to revise your forecasting model. Maybe the forecasting model was completely off. That's why I made bad decisions, and therefore I got a loss. Okay. So given that feedback, you again enter the for loop, again build a better forecasting model, take potentially better decisions, and hopefully get better feedback, and therefore you know that you're doing better over time. So you just put things in for loop, and that's where reinforcement learning comes in. Okay. So if you're not doing reinforcement learning, that's fine. You may still be making complex decisions, except it may be one-shot decisions. Okay. I mean, especially long-term decisions, you don't have to put them in the reinforcement learning context. It could be one-shot decisions. Okay. And so here in the next few slides, I'm just showing you some complex decisions which arise in engineering, right? Some of you have done engineering degrees, so things which arise in engineering, in machine learning applications, actually in healthcare or finance and so on. Sorry. So engineering decisions like flying drones or autonomous driving. So I was talking about inventory management, and of course ML has a huge application area in clinical decision support and healthcare, and logistics like transportation scheduling, like even matching you with a Uber or a Lyft driver. Okay, there's some decision to be taken, and it's not just a myopic decision between you and a bunch of drivers. There's a lot of other offers and a lot of other customers and a lot of other drivers. So you have to do some sort of a matching. Okay, matching is a technical, I guess, word in computer science. You might have heard of matching problems or things like bipartite matching and stuff. And also, I guess one application of doing complex decisions is games, where you may want to take long-term decisions and not myopic decisions. Myopic just means like immediate reward fetching decisions versus things which are long-term. Okay. And for these types of decisions, if you can improve yourself, as in you can maybe in real world you can deploy decisions and get some feedback, or you have some simulation where you can try decisions and get a feedback. Okay, maybe there's a finance simulator which will tell you, if I do this portfolio, it will tell me how well that portfolio works. It doesn't have to be real world itself. As long as you can get feedback and you can try different things and improve yourself, then that falls into the domain of, I guess, reinforcement learning. Okay, that's where the reinforcement aspect comes in. There's this feedback, and therefore you will reinforce your beliefs about what could be the model of the world and what could be my better decisions. Okay, and that actually has intersections with engineering, because especially control engineering, they have been, we've been flying aircrafts for a long time, even military, weapons and things, what is it, drones and so on. It has intersections with ML, right? ML, AI, and even operations research area, and it has intersections with psychology, which actually prompted these type of, I guess, these types of names, reinforcement and so on. Okay, and ORs, which I just mentioned. So those are the areas, and here's again, just snapshots of things. So I think last time while motivating, I mentioned this game of Go where software system beat world player. It was very difficult actually. 5 years ago it would not have been possible, just because of the complexity of that particular game. Even though it's not stochastic, nothing is random there. Everything is deterministic. But your action now will influence, what's the situation of the game tomorrow and so on. So there's long-term consequences, right? A big area is ad placements, which some of you, I mean, we also discussed this in the last lecture. So here you want to know about user behavior, okay, what improves engagements and so on. Sometimes the metrics are wrong, so it completely optimizes for wrong things, but those are application areas. And last time I mentioned there is this, the I guess, new interest in reinforcement learning. Reinforcement learning is there; it has been there for the past 40 years or more than that. Actually, is because in 2013, DeepMind demonstrated human level performance, or better than human level performance, on a bunch of games. Okay, and these games are not myopic. Again, as I said, your actions in current situation influence what's going to happen in several I guess, time periods later. Okay.
Self-learning, so is it related to that, or if not,
Self-learning. What is self-learning?
I mean, so if you make a wrong prediction,
yeah.
So you don't train it again, the model again. So it learns on its own that it made a wrong decision based on the inputs.
Yeah.
So that's what you're saying RL is doing. So when you say self-learning models,
I didn't say self-learning, but so RL systems have just one thing, right? So as we saw last time, there was a context. Like, think of contextual binaries. There was a context. We took a decision. We got a feedback for what decision we took. There was no loop back saying that because of the decision we took, a new context dependent on what decision we took and the previous context would come. Okay. So here the context is going to be dependent on what decision you took and which context. Okay. Next context. So, and also there's going to be a reward or a feedback that depends on what you did. Okay. So it's just based on that. That signal is going to help you learn. Okay. Now this is not probably called self-learning. I think in the game of Go, not in Atari. Okay. The game of Go, the software system was trained to play against itself. So it played against itself to improve itself. Okay. It's called self-play, to improve its own understanding of the game and therefore do better. So, but we'll get there maybe next lecture. No, it's playing against a copy of itself in that game. Yeah, so the copy of itself is like the environment for it. Okay, it's a game situation. It's different from, I mean, this is also a game situation, but here you have few actions, left, right, jump, and so on, and then there's a monitor, a simulator, a computer program. It's telling you, oh, you did fine, or this is the next state, and so on. So there is some similarity, but self-play is slightly different. So we'll get there next time. Okay. Actually, I have a copy of this. I think Atari. Yeah, I think maybe this one. So this is a game called Breakout. Okay, and you are supposed to not drop that ball, which is just 1 pixel, I guess. And here they're showing a particular algorithm which is based on Q learning, which we'll study today. which is able to try different things. Sometimes it fails, and then after lots of training episodes, okay, which we'll discuss what episodes are and so on, it's able to balance the ball and get reward. So for it, the feedback is going to be the score at the top. Okay, it tries different actions at every frame of this. It's seeing it as a visual thing, okay, just like human, and it's able to see the score, whether the score improved or not, and different actions let it improve the score. And so finally, it is figured out what's the best thing to do, best action, okay, best decision to make, and these are long-term decisions, right? So that's breakout. And actually, one of the teams worked on this, tried to work on this. I haven't seen the report. So this is called Flappy Bird. How many of you haven't seen this? Okay. So this is just a game where, again, you have to control the height of this bird. Okay. And you can actually, so a simulator can give feedback on, depending on the action you took, how much did you jump and so on. It can tell you what the next state is and whether you made improvement in terms of score. Okay, and you can actually read the score, see that as a feedback, and improve yourself over several experiences or several episodes. Okay, and then we saw the full self-driving video of Tesla, I think from last week, as a PR thing, but so the guy sitting here doesn't actually touch the steering wheel at all. Okay, it takes all the merge actions, highway, stop, turn actions, and everything. And even if the car's next to it, it still manages to drive, right? So this is not just based on one simple algorithm. There's a lot of engineering effort that goes in, but a part of this is a huge control system. Parts of it for such an autonomous system could be trained using some of the things that we'll see today. Okay. Anyway, we'll see some videos later. Let's come back to this. Okay, last time I just mentioned this Go thing, and actually next time we'll actually look at a little bit more details about this computer versus a Go player. Okay. So yeah. Okay, so in terms of how we are progressing, okay, we're going from actions to rewards. So there were some 10 actions, and we were just trying to figure out which action is the best. If you just focus on learning, then you would spend equal amount of time trying out the different actions, and you'll get some estimates. And so all the estimates will be better and better if you try them more and more. And so that's just estimation. Okay, the way decision making is coming into the picture is that you want to estimate while not losing money while estimating. Okay, so if you take a bad action several times, then on all those number of rounds, you're actually losing money. Okay, in terms of you're not getting reward. Okay, so there was this additional target that we cared about, which was the minimizing regret. Okay, and so we wanted to learn while minimizing. Actually, we cared about minimizing regret, and learning was a way to do it. And we saw a few algorithms to which achieved this learning plus earning objective. Okay, so we saw upper confidence bound, Thompson sampling, epsilon greedy, and some variations like that, right? So that was multi-on bandit. So it's one example of a sequential decision making setting. Okay. Anything in the for loop, I said, whenever you have a forecasting plus decision making with a for loop in is essentially sequential decision making. Okay. And the next version that we saw was contextual bandits, where there is an additional notion of a context or a state. Okay, the state. So you prefer in different states to take different actions rather than the same action irrespective of what state it is. Okay, if you ignore the state, then it's just multi-on bandit. But if you care about the state and therefore take actions, then it's called contextual bandit. Here also you care about taking the best actions in the context, in the appropriate context, and therefore getting as much reward as possible. If you knew what's the best action to take in each context, then you're done. But you don't know a priori what action will lead to how much reward. So in each context, you may also have to try different things. Okay, you may have to try potentially try a bad action to learn that in this context I'm taking a bad action. So we are able to still learn in this because of one property that we saw with especially EXP4, that maybe multiple policies which map from context to actions. There could be multiple policies which in the same context map to the same action. Okay, then we can exploit this aspect that okay, even if I tried a policy 1 for how well it performs in this in this round, I can learn about other policies which are similar to this. Okay, so that was the kind of very high level intuition for why EXP4 or contextual an example contextual bandit algorithm that we saw works. Okay, so if you didn't get that intuition, just go back and see that learning for a policy, we are at the same time we are learning about other policies. Policies are just mappings from context to actions. Okay, in that case, and we'll actually see policies again this time in subsequent slides. Okay, now what's the block level picture of what's happening with reinforcement learning is that two things. The first thing is that the action that you take may not immediately lead to a reward. Okay, so me setting up the infrastructure for my let's say brick and mortar store will not immediately lead to sales on day 1. Okay, but there's going to be a long-term effect of this setting up the infrastructure on infrastructure, right? That action that I took is going to be potentially increases in sales across maybe multiple seasons. Okay, so that means that's the difference from the previous two settings where the moment you took an action, immediately you got some reward. Okay, that was the assumption in those two settings. That's the first thing. Second thing is your action is going to influence what's the state of affairs tomorrow. Okay, if I already improved my brick and mortar store today, of course tomorrow I don't have to do that action because it's already in a pretty improved state. Okay, similarly, let's say you are this is a bad example, but let's say you're a pension fund and you or let's say you're Vanguard and you really invested a lot into like a new S&P 500 entry, okay, some new tech company, then that's going to influence the state of affairs of the world, right? That's going to influence the stock price of that entry as well as other securities and so on, right? So all I'm saying is that there are some situations where actions influence what's the situation of the world tomorrow. Okay, and I guess a more simpler example is robotics, right? If you take an action of moving forward, then tomorrow's state is that your location is now different and it's going to be that forward location, right? So that's a very simple example of your actions influencing the states. Okay, so that's the second aspect. And so under these two additional aspects of the problem, how do we learn good ways to make decisions? Okay, the decisions are going to be essentially actions. And again, we'll learn things called policies, which are mappings from states to actions. Okay, same thing as contextual bandits, where we are trying to learn. I guess in the EXP4, we're learning a distribution over these policies, but here we're going to again learn a policy which may perform well. Okay. So again, those were just very high level slides in just connecting it to previous lecture. Now what we're going to do in the next 4 or 5 slides is ground the RL problem. Okay, what are the building blocks of the RL problem? That's the first goal of today's learning goal, right? So it's an example of a sequential decision making setting. So for loop with forecast, decide, get feedback, forecast, decide. Okay, now there's going to be an environment, and that's the that's the entity which is going to give us feedback. Okay, and also it will change its state. Okay, and agents takes actions in this environment, and the actions influences the future. Okay, so that's where I said the action that I take today is going to influence what happens in the next time period. Okay, and the agent may potentially get a feedback signal. It could be immediate, it could be delayed. Okay, maybe it's several time periods later, or it could be now. Okay, so if you don't take an exit when you're taking a highway and you don't take the exit now, you have a long-term consequence for the next 15 minutes. You will still find the next exit and then reroute yourself. Okay, so there is a long-term consequence. So those are I guess keywords: environment, agent. There's an influence to the future, and there's potentially delayed feedback. Okay, and what's the goal? The goal is to select actions, so make decisions, select actions, make decisions to maximize the total reward. Okay, and this was the same objective even in the previous lecture. Okay, maximizing rewards was essentially the same as minimizing regret. Okay, and RL framework, the framework of reinforcement learning, or the way to think about things as reinforcement learning, provides several answers, to good enough answers to this question. Okay. So let's look at the environment a little bit. So let's assume that the agent's action at time t can be represented as AT. Okay. And so let's say agent took an action AT, then the state of the environment changes to ST plus 1. Okay. So currently it was ST, let's say it went to ST plus 1, and we generate a reward RT plus 1. Okay. So notice the index. So action AT generates reward RT plus 1. That's just notation convenience. I could have pushed T plus 1 to T, but that's what this is. And T indexes time. So measurements, when you're making measurements, okay, days, weeks, minutes, whatever resolution you're working with. And the current observation is called the state, okay, or the context. And one of the assumptions that we'll make, it's not very, this assumption may fail in some settings, but the assumption is that the probability of the next state given the previous states only depends on the current state. Okay. So the probability of going to ST plus 1 given ST, actually I should also add here given AT, okay, given the action that I took and in the current state, okay, me going to state ST plus 1 does not depend on what all states I visited in the past. Okay, that's called the Markov assumption. So all these don't matter up to this time. Okay, AT matters because AT may matter or not. Okay, and so this is the Markov assumption, and this is the assumption about the environment. So the environment is essentially some sort of is generating random variables. Okay, it's generating the state random variables. It's just saying if you do something here, I'm gonna just output to you ST plus 1. If you do something else here, I'll output some other ST plus 1. Okay, if you do some other action, that's all. And it need not be even be stochastic, it could be deterministic. So if, for example, on a chessboard, if you take an action of moving the knight from something to something else, then that's the new state is going to be deterministic. It's exactly going to be where you moved the knight to. Okay, so that's also, that's a special case or a degenerate case of this stochastic assumption. Okay, so that's the environment. That's one piece. What's the agent? The agent observes two things, right? If it take an action AT, it observes RT plus 1 and ST plus 1. Okay, and these observations are not IID. IID just means independent and identically distributed. These observations are not IID because what RT and ST were influence what, maybe not RT, but what ST was influences what ST plus 1 was, right? It may also, and AT also influences what ST plus 1 is. So there's a temporal dependence across time. Okay, that's what they are not independent. Okay, and the agent's objective, explicitly writing it, is going to be this. Okay, it wants to maximize the expected total reward. Future is just because I'm taking action AT at this point of time. I want to take the action which maximizes my total expected reward. Okay, I don't want to be just myopic. I don't want to get the most reward now. I care about today's reward, which is RT plus 1, plus some let's say gamma is 0.9. 0.9 times tomorrow's reward plus 0.9 square times the day after tomorrow's reward, and so on. Okay, if we can write it that way. And so there's an expectation here because these rewards could be random, right? Because of the transition probability dynamics, because of the environment being stochastic, as well as the reward itself being stochastic. That stochastic just means random. So because of those two, there is an expectation E here. Okay, and I'll discuss this a little bit more in a few slides. Okay, but agent has to just take actions. Its objective is to maximize the total reward. Okay, that's what you want to get away from this slide. Okay. And I guess another very high level point that you want to get away from this slide is that the agent may want to trade off getting current reward versus getting more rewards in the future. So you may take a action which gives me only $1 today, but gives me $100 from next week onwards. Okay, whereas a myopic agent or agent who is not long term oriented would get the $5 today and forget about all, get zeros later on. Okay, so that's something, that trade off, temporal trade off, the agent has to make, and the agent is essentially the software, right? Okay, that's our virtual agent, or that's our software. And what's the reward? A reward is just a, RT or RT plus 1 is a scalar. It's a number. It's a there could be variations in this treatment. I'm just going to assume that they are numbers. Okay, it just indicates how well the agent is doing at time t. So it could be monetary reward, it could be sales today, sales tomorrow, and so on. Things like that. And as I said, agent's job is to maximize the sum of these rewards, okay, across time. And yeah, so this is not very critical. So reinforcement learning idea is based on that there is this, everything can be boiled down to maximizing some rewards, bunch of rewards, and in fact the agent is caring about this sum of these rewards, or cumulative reward, okay, cumulative discounted reward. Yeah, so this is what I said, select actions to maximize total future reward. And as I said, rewards may be delayed, and we already saw that, and actions have consequences in terms of states. Okay. States are the next context that I see. Okay. Okay, that's fine. So again, to very high level, drill down the basic idea. You have the agent takes an action. So this is this way. That's the input to the environment. If you just think of these as functions, let's say, or state machines, agent sends a AT to the environment, and the environment responds with so environment, let's say, sends st comma RT, then agent takes an action AT. Okay, first this happens, and then the next this happens. Okay, and then if the agent sends this, then you get back st plus 1 and RT plus 1. Okay, that's the interaction. As I said, it's the same. So you sent AT this way, and then you got st plus 1 and RT plus 1 this way, and so on. Okay, is that interaction clear? Okay. So what's the difference? Okay, with supervised learning. In supervised learning, you have the training signal. So you have inputs and training signal. Training signal, just think of them as labels in your training data. Okay, so you already have the training signal, and you have inputs, and you care about building a function, prediction function that makes the outputs as close to the training signals as possible, right? That's the f of x is as close to y as possible, right? Whereas here you have inputs. This is going to be the state. Okay, there's an RL block or an agent or an algorithm. It generates outputs, and these outputs are now actions. These are decisions. Okay, they are not related to any labels. They could be labels as well in a special case, but they could be general actions. And then the actions are passed on to the environment, and the environment produces a training signal, and that signal is going to be RT plus 1. If I take an action AT, the signal is going to be RT plus 1, and the RT plus 1 is not the state itself, right? So environment generates RT plus 1 as well as generates the next input, which is ST plus 1. Okay, the current input is ST, it generated AT. Okay, and then I get a training signal, and I get the next input as well. So it's a little bit of an online, it's a different or I would say a little bit more general than supervised learning. Okay, but they are slightly different settings anyway, right? Supervised learning, you may have batch data and you want to get a model. Here it's not really batch data. You can think of it as something you're trying to do online. Okay, and there's some consequence. This part is not there in supervised learning, right? And these are just trainings. This could be just labels in supervised learning. Okay, those are the two variations. Okay, so what constitutes an agent is that agent may think of several things. Okay, first thing is the agent. The agent has to act, right? Has to take actions AT in every round. So the agent will need an object called a policy. What is a policy? It's similar to contextual binaries. It's going to be a mapping from states to actions. So mapping from context to actions. If the agent already has a policy, then they can just execute the policy. As in, see every new context or new state. Just look at the function, where does it map to, which action does it map to, and just output that action, right? The agent may also want to think of what are called value functions or values. Okay, what are values? And we'll discuss more about values pretty soon. Okay, several times. These are going to be, if the agent understands how good is each state to them. Okay, how good is each state, or how good is each action in a given state. If they have some notion. Okay, if they can attribute, okay, me being in this state and taking this action is really good, versus me being in this other state and taking that action is really bad. that kind of can help them make decisions. Okay, and this we'll see more clearly in a few slides. And the last part is agent can just understand how the environment behaves. If the agent can just know what is the probability of st plus 1 given at and st, then the agent knows how the environment behaves. Not just this, but also how does the agent generate rewards, right? So how does the agent generate rt plus 1? Okay, so if the agent knows this, then it doesn't need the environment. Okay, it can just figure out what's the best thing to do if it knows the model of the environment. Okay, that's what I mean by model. Okay. So policy. So policy is characterizing the agent's behavior. There are two types. For example, a policy is just a function which goes from s, which is the context or state, to an action, or it could be what is called a random policy. Okay, random policy just means that in the given state, I may have a probability distribution over actions that I can take, which just means if I have two actions, I can flip a coin and pick one action or the other. Okay, so that's also a policy. So in a given state, I don't know how much what to do. A stochastic policy will say, okay, with some probability do the first action, with some probability do the second action. Okay, that's an example of a stochastic policy. Or deterministic policy just says in this state just go left, just go right. If the robot is already at the cliff, then don't go and jump, fall over the cliff, go the opposite direction. Would be a deterministic policy, for example. So here's an example in what is called a maze, right? So here you have this maze. So white blocks are where you can enter. So your state is going to be which location, which cell you are in, which white cell you are in. Okay, and your actions are going to be north, east, south, and west, right? Left, right, up, and down. And at each time, if you're not at the goal, let's say I subtract -1. Okay, just trying to ensure that you try to reach the goal as soon as possible. Okay, and here is a policy. Okay, so this is a visual representation of policy. It just means that if I'm in this state, go north. If I'm in this state, go west. Okay, if I'm in this state, go south. Okay, that's all it means. That's a representation of a function. If you're in a certain state, do something. Okay, and yeah. So any questions about policy? I mean, we've already seen a policy last time when we talked about contextual bandits, but any questions about policies? Okay. So the second object is probably something that you have not seen before. It's called a value function. Okay, it's a function because it ascribes a number or a value to, for example, every state. Okay, so value function is a function which ascribes a number to every state. Okay, so let's say pi is the policy. Okay, subscript not yeah. So pi is a policy. Okay, so v pi of s is going to give a number to every state, and what is that number? That number is going to be this expectation. What is it saying? Starting from this context or this state, being at time t at this state, you'll get some reward. Then you'll be in some other state. I don't know what the state is, but at that state, you will use the same policy to figure out what is the action. Take that action, you'll get some reward, and you'll go to some other state. At that state, again, apply the same policy. Okay, and I'll give you some action, and therefore you'll go to some other state. Okay, so in that way, you'll generate all these rewards. And I'm just adding some discounting. Think of this as 0.9 or 0.5 or something, some number, fixed number. Okay, so a value of a state is just the sum of rewards, discounted rewards. Discounted just means that this gamma is less than 1. Sum of rewards, sum of expected rewards that I can get from that state. So a state is good if from that state, if I execute this policy, as in keep applying this policy every time I hit a new state, I'm getting good really good rewards. Okay, really good rewards. That's all. So a state is bad if from that state, if I execute this policy, I'm going nowhere. I'm falling off the cliff or hitting dead ends. Okay, then that state is bad. That's all. And it's also, I guess, it's a prediction of future reward, because what we care about is this. When we take actions, remember the RL agent's goal is to take actions to maximize rewards. over a time period. Okay, and so this is a proxy, or this is a prediction of the future reward that you can get. Yeah.
The discounted values are determined based on?
So I'll tell you what the discounts can be, but so this is like discounting today's money versus tomorrow's money. I don't know. Do you know time value of money? Some of you know. Does anybody know time value of money? Yeah. What is it about? What is it about?
So there are a lot of factors that influence.
So money. Yeah. So money today is worth less tomorrow. Like if I give you $50 today, if I give you $50 1 year later, that $50 1 year later is should ideally be lower worth to you. Okay. So discounting here just means that reward today is a little bit more valuable to me than tomorrow's reward. So whatever reward I get tomorrow, I'm going to discount it less. Okay, discount it by this multiplier. It's just like we saw loss function plus regularizer, right? So there was a multiplier c or some constant or lambda or something. It balances two objectives, right? Remember in supervised learning we had this loss function plus some regularizer with a constant in the front. The constant in the front balances two terms. Here same, the discounting parameter gamma is balancing how much do you care about reward, next day's reward versus day after tomorrow's reward versus 2 days after reward. Okay, that's all. Any other question? Okay. So what's the value function look like? So as I said, it's a number assigned to a state, and for me in this maze example, every state was just a coordinate, right? I mean, xy coordinate, let's say, right? So for every location, so every white cell, I have a number. So somehow in this case, I have computed the numbers. Okay. So it's according to a particular policy, pi. Okay. I haven't shown you the policy, but you can imagine what these numbers are. So for example, if I'm in this state, right, I will reach the goal in one step, and if I take one step, I know my reward is -1. Okay, and the policy was, if you remember what the policy was here, the policy was go right, right? So it is actually in that state, just go right. To go right, I can go right and reach the goal, and for that I'll get a value of -1, and that's it. There is no more reward once I reach the goal in this example. So my value is -1. Okay. And similarly, you can backtrack all the way and see, if you're the starting position, you have a quite bad value, which means that this is not a good state to be in. And in fact, if you go really badly, do some dead ends, then it's really bad state to be in. Like -22, -23 are bad situations to be in. Okay, that's just the worth of that state. Okay, each of the states. Yeah.
So if you didn't know the value of each state, then
yeah,
you try and error such that you learn the value of the state.
We'll get there. So right now I'm just saying. We said an agent can either think of policies, I mean learning a policy which is directly mapping from state to context to actions, or it may think of assigning values to states. Okay, which state and which action is good, which state and which action is bad. So we're just understanding what values are and what policies are and what model is, and we'll get to how we what do we do with this, whether we learn, how do we learn, and all that soon. And the third component, so we saw policies, we saw values, and now we're going to look at models. What is a model? Model is just predicts what the environment will do next. So we said environment pretty much spits out the next state and spits out a reward. Okay, those are two things that the environment has to produce. So if you can just produce it yourself, you don't need the environment, right? So let's call script P the prediction of the next state. As in prediction just means just the transition probability, let's say matrix or something, which given the current state tells me what's the probability of being in state, next state being this, that, or something else. Okay, and R predicts the next reward. Okay, so basically what is, as I said, RT plus 1 reward could itself be random, a little bit random, right? Sales could be 10 units or 20 units or anything in between. So what is the expected sales you can have given that you took certain decisions of shelving your of putting certain products in your store, for example, right? So the script P is actually script P for an action going from state S to S prime. So this is just a transition probability matrix, right? Or transition probability object is just saying if I'm in state ST is S and AT is A, what's the probability that ST plus 1 is S prime? Okay, so think of two states, two actions. Okay, then it's just saying if I'm in state 1 and action 1, then what's the probability of me going to state 1 again or state 2? Okay, that's it, 2 numbers. Similarly, if I have 2 other numbers being in state 2 and action 1, then what's going to happen? So this object you've seen lots of conditional probabilities in graphical models. So this is familiar to you, and this is just the expectation of reward that you can get if you are in state ST and you took action 80. Okay, these are just general. So your reward need not be stochastic, then you don't need this expectation. Okay, but in general we are writing it as with expectations. So yeah, so in this plot I'm just showing the rewards. So r t plus 1, it's always -1. So whatever I do, whether I go up, down, left, right, it's -1 is the reward. Okay, and in this case, if I want to go left or want to go right, there is no probabilistic transition to the next state. It's literally go to the state next to it. Okay, so if I'm in let's say if I'm in this state, and if I want to go to this state, if I go right in this case, then I will definitely go to that next state. Okay, there's no conditional probability here. In the sense, it's conditional probability of me going to the left state is exactly 1, and me going to the right state is exactly 1, and one going to the left is 0, because I took a right action, let's say, or going to the east action. Okay, so any questions about the 3 things that the agent can think about? Okay, while taking decisions. These are 3 things that agent could think about. Then we'll look at what's the learning, what's the learning aspect of this whole problem. Okay, any questions so far? Was it too slow? Okay, so let's look at some basics. Okay, so I introduced those 3 ingredients because now we're gonna think of a framework, just like maximum likelihood estimation, essentially like a framework to view these things. So we just discussed policies, value functions, and models. Okay, so these are the symbols I'm going to use. Okay, and first we'll discuss what is a Markov decision process. It's just a way to think about all these things together, and then we'll address the question of optimizing for the best policy. Okay, if we know the best policy, then we'll get the most rewards, and therefore we'll maximize the expected total rewards, right? That was the goal. Okay, so we don't know the best policy, and so what we'll do is try to learn the best policy while exploring the environment, and that's reinforcement learning. Okay, so we'll try to learn the best policy while trying to not we'll try to learn the best policy, essentially. That's what we want to do by interacting with the environment. Okay, that's the goal, eventual goal. Okay. So MDPs are just a useful way to describe an RL problem, and we're going to do it in this progression. First, we're going to start with the Markov chain. So we studied Gibbs sampling in the inference part of graphical models. So we're going to revisit. So in fact, right now we'll take a very elementary look at what a Markov chain is. Okay, and then we'll look at what is called a Markov reward process. It's just one additional attribute on top of a Markov chain. And then we'll look at what a Markov decision process is. It's one more additional attribute, which is the notion of actions or decisions on top of a Markov reward process. So that's the progression. So Markov chain should be easy. Markov reward process is relatively one additional attribute, but Markov decision process is just with decisions in the mix. Okay, so let's look at Markov chain. So Markov chain is defined by just this type of conditional probabilities. Okay, and so either you can write it this way, probability of going from S to S prime, or you can write it explicitly as a matrix. Okay, probability of me being in state 1 and going to state 1, probability of me being in state 1 and going to state n. Okay, so each row is a conditional probability. Okay, think of everything as discrete here and finite. So I only have n states. So I'm in state 1. What is the probability of me being in state 1 next time versus me being in state 2, state 3, state n. Okay, so that's the probability matrix, and here's an example representation of that Markov chain. Okay, so here we just saw, okay, what's the probability of me going from state 1 to state 2 or whatever. Here's a diagrammatic representation. Okay, so here there are few states: Facebook, sleep, class 1, class 2, class 3, pass, and pub. Okay, and these arrows represent the transition probabilities. So if I'm in let's say class 2 state, outgoing arrows represent what I'm going to do with some probability. Okay, it's a completely it's a Markov chain, so you're just observing the chain. Okay, there's nothing to control here. Let's say in this example, so I'm in class 2 with 0.8 probability I'll go to the next class, or 0.2 probability I'll go sleep. Okay, so that's the chain, and this chain actually has what is called an absorbing state. Sleep is the last. From sleep you're not going anywhere. Okay, so this is only for the day, I guess. So till you hit sleep, you do some transitions. Okay, for example, in the first, so let's say you always start with first state being C1. Okay, then maybe you went to class 1, class 2, class 3, and then some state called pass, and then you went to sleep. Okay, or you could do other things, right? You went to class 1, then you went on Facebook and some more time on Facebook, and then class 2 came back to class 1, and then class 2 and sleep. Okay, so these are and each such string of transitions till you hit some, maybe what is called an absorbing state is called a episode. Okay, or you can also always terminate after 4 such transitions and call it an episode, anything. So it's fine. So it's loosely defined here. So this is an example of a Markov chain. Okay, and these are the states that are being, so this is the index, right? S1 is this, S2 is this, ST is this. Okay, and so that state, this diagram, the numbers on this diagram are essentially this is the P matrix. Okay, script P matrix, which was I guess 7 cross 7. Okay, so each row sums to 1. So that's Markov chains. That's fine, and you should connect it back to Gibbs sampling. By the way, in Markov Gibbs sampling, each state is going to be an assignment to the probability distribution. Okay, if you're doing Gibbs sampling, remember in your assignment you were doing Gibbs sampling on a Gaussian mixture model. Then each state there is x comma this lambda. So lambda is taking one of the 10 values, and x is just a Gaussian, it's a one-dimensional Gaussian. So that's your state. Okay, I mean there you cannot really enumerate the state, but that's what a state is. So x comma gamma is a state, and so there's a transition from x comma gamma to x prime gamma prime, x double prime gamma double prime, and so on. So all those transitions happen in a dependent way, but eventually you're getting samples from the actual mixture of Gaussians. Okay, so there is some stationary distribution related to the Markov chain. Here we don't need the notion of stationary distribution stuff, but there is a notion of stationary distribution. Okay, actually here you have a sleep, which is an absorbing state. So the stationary distribution is a degenerate distribution with 1 on state sleep and everything else being 0. Okay, if you care about it. But anyway, let's move to Markov chain with rewards. Okay, there's only going to be 2 additions. So one addition actually. So there's states and transition probabilities between states, right? It's still, we're just observing it passively, nothing to control. What we'll add now is this object. I'm representing it as R, which are rewards. Okay, and a discount factor gamma. So we just discussed discount factor. So rewards are nothing but, so as the Markov chain is transitioning from states like class 1, class 2, class 3, pass, sleep, something like that, we are also seeing a bunch of rewards being generated. Okay, they're completely determined by the states. We are not touching anything, we are not acting on anything. Okay, and the reward function is nothing but the expectation of potentially a random variable given a state. So it just depends on the state. If I'm in class 1, maybe I'll get a reward of +1 in terms of learning or whatever. In class 2, +2 of learning or whatever. Okay, so those are rewards. I'm just observing the rewards. So that's called a Markov reward process. Okay, MRP. And gamma is a discount process. As I said, you may discount rewards 10 days later versus rewards that you get today. Okay. And so in this MRP, we can define another random variable called GT, and you can see the form is similar to what we thought about value function. So actually GT is just going to be the total discounted reward from time step t onwards till the end of time. Okay, maybe the end of time is infinity, then it's all the rewards I can collect. Or if the end of time is some 100 rounds later, 100 time steps later, then that's it. Okay, so GT is called the return random variable. Okay, it's just the total discounted rewards. Okay, and discount is useful when there is infinity, because if rewards, if all these R1, RT1, RT plus 1, RT plus 2, all of them are bounded, as in let's say they're all at most $1, and if I do an infinite sum, $1 plus $1 plus $1, it's going to be infinity. But if we put a discount, then it's not going to be infinity. Okay, that sum, infinite sum, is going to be 1 times 1 by 1 minus gamma. Okay, something like that, some finite number. So that's another way discounting helps. Okay. And if you take an expectation of this random variable gt, which is a bunch of random sum of bunch of random variables as well, then that's called the value, okay, value of a state, right? Remember, value of a state is just the expectation of this return random variable starting from a state st is equal to s, okay, that's the value of that state. Okay, so even with just a Markov reward process, we can define what is the value of a state. How good is a state? Is just the sum of the expected sum of the rewards that I can get from that state onwards. Okay, I don't want to go through the example, it's just the discounted sum there. Now here is a nice trick which will be useful for us when we talk about Q-learning eventually, which is as follows. Okay, so the value function v of s can actually be written in a recursive manner. Okay, you've seen, how many of you have solved Fibonacci series programming problem? One, just two people. Okay, several of you. But anyway, so you understand the notion of recursion, right? So factorial function, is you can write it as a recursive function. So here, we know that v of s is expectation of gt given st is equal to the current state s, right? So we can expand that out. So that's this term. We can take gamma common for that second term onwards. Okay, and from second term onwards is essentially gt plus 1, right? It's the cumulative reward from that time step onwards. Okay, and gt plus 1, it's going to start from some state st plus 1, right? It's not the current state, but whatever state was where I landed in the future, right? So that's just the value of that whatever state I landed in the future. Okay, so value at the current state is take the average of whatever states you land in, reward, and the value of that whatever state I land in. Okay, that's the recursive equation between value at a current state versus value at a future state. Okay, any questions about this recursion? Okay. Okay, so the same thing so you may be wondering, like, what is this expectation covering, right? So let's demystify that. So here what I'm showing is explicitly what this expectation is. Let's just focus on this last equation. This diagram is just showing, okay, if you're in state s, you may go to state s prime, which is let's say there are only two states in the system, then you can go to state a or state b. Let's say you're in state a at time t, then you can go to state a or state b. Okay, the average of them is what you should consider. Okay, in the recursive equation. So value of s is immediate reward that you can get from that state plus all the states you can go to, let's say a and b, times the value of that value of a and value of b. Okay, so probability of me going to state a from here times value of a, probability of me going to state b from here plus value times value of b, the average of them. That's what this expectation means. Okay, we just explicitly wrote it. Okay, so that's recursion. And why did we discuss recursion? Later on, this is going to help us think of algorithms. Okay, what is called value iteration, and then Q-learning. Okay, and Q-learning is the basis for like Flappy Bird and all that stuff that we saw, Atari, Breakout, and all that. So we want to get there. We want to understand how Q-learning works. But for that, we need to understand these elementary blocks. Okay. The last addition to the Markov chain, Markov reward process is going to be the notion of actions. Okay, so nothing has changed except for one additional object, actions. So let's say script A is a set of actions. Then we're just going to augment that state transition equation. So I'm in state S. If I take an action A, then I'll get to some state S prime with some probability. So it's just the additional conditioning on action A. Okay, so there's additional conditioning on action A. Similarly, there's going to be an additional conditioning on action A for how I get a reward. So if I really do a good job, then maybe I'll get a lot of money. But if I don't do a good job, that action, then maybe I'll not get money. So rewards also depend on actions, and next state transitions also depend on actions. Okay, and rest of it is the same. And so this is a different Markov chain. Okay, not the same as what we saw in the first slide. So here my actions are written in red. Okay, so if I study, I'll go to some other state. So let's call it state A, B, C, D, and E. Okay, these are not the same as previous example, but if I'm in state A, I study, I go to state B with a reward of -2, and if I'm state A, I do Facebook, then I get to state D with a reward of -1. This is an example of a Markov chain. Okay, and so that was an example of Markov addition process. And now we can, since we introduced the notion of actions, now we can talk about policies. Remember, so we already had states, now we introduce actions, and therefore we can say, okay, what's going to happen when I introduce a policy, which is mapping from states to actions. Okay, so a policy, remember, is just a distribution over actions given states. So this is the most general way of saying it, but just if you don't care about distribution, just say if I'm in a state S, I'll take a specific action A. Okay, that's a deterministic policy. Here I've written a stochastic policy. So in a given state S, I'm going to take a specific action. So now we are explicitly, now we are being active members. Okay, so Markov chain, Markov reward process, there is nothing to do, completely passive. We introduced Markov addition process, we introduced actions. So now we are actively partaking in how we'll get rewards. Okay, so that's the important aspect. And so this policy fully determines the behavior of an agent, by which I mean that if I tell you the policy, then if I tell you the policy and the policy is fixed, then I just have a Markov reward process. Once I tell you, okay, in this state do this, in this other state do that. So if there's a bunch of rules like that, then there's nothing else for me to do because I've already told you what the policy is. Then it's just a Markov reward process. In every state, it's just transition to some other state according to the transition probabilities that we define, and we'll keep getting rewards. And that's because we fixed the policy. Okay. So if a policy is given, then the state sequence is a Markov process, and the state and reward sequence is a Markov addition process. Sorry, Markov reward process. Okay. And so if it's a Markov reward process, what's the state transition? It's going to be what's the probability that you're going to take a certain action, and if you take that action, what's the probability you're going to go to S prime? Okay, that's how you can compute the transition from S to S prime. Okay, you just add over. Oh, I'm going from S to S prime. Oh, how would I get there? If I'm an S, if I take an action A, maybe with some probability I'll get to S prime. If I take an action B, I'll with some probability go to S prime. I just average all those probabilities. That's the probability with which I go from S to S prime. Okay. Similarly for rewards as well. Okay, in that state, what's the reward? Average of all the actions I took and whatever rewards I could get. Okay, so we have that. So we said MDP with a fixed policy is a Markov reward process, and so let's understand value functions in the MDP context as well. Okay, it's the same quantity, but we just reinterpret it. Okay, so the state value function v pi of s is again the same thing. It's just the expected return random variable, expectation of the return random variable. Remember, return random variable is the sum of the discounted rewards. Okay, expectation of the return random variable given the current state. Okay, so that's the same as before. We just revisiting the definition. Okay, but the next value function will be slightly different. Okay, we can also define what is called the state action value function, or the action value function. Okay, it's going to be represented using Q. Okay, it's going to take two arguments, S and A. Okay, so it's different from the value function in the at the top, which is just the expected sum of discounted rewards. Here, this value function is still going to be the expected sum of discounted rewards, but you have to start from state S and take initial action A. Okay, so the difference here is both are, given a policy, the value function at the top is saying, given a policy, I'm in state S, apply that policy, go to some other action, like policy will tell you what action to take, go to the next state, get some money, apply the policy and keep going forward and get rewards and average them, right? The bottom value function is saying, okay, starting from state S, take a specific action A. Okay, don't apply the policy immediately. Take a specific action A, then get to some state st plus one, and then from that point onwards apply the policy. Okay, it's just a little bit of delay in applying the policy. Okay, that's why there is a second argument, because I also need to decide what action I wanted to take today. Okay, whereas in the first one, I'm not telling you what action to take today because pi will already tell me what action to take. Okay, that's the difference between these two. And this action value function will be important for us when we talk about Q learning. So that's the Q here. Okay, and just like we saw recursion equation in the Markov reward process, I'm just rewriting the recursion equation here for the Markov decision process as well for a given policy. Remember, for a given policy, it is just a Markov reward process. So it's the same equation with an underscore of pi. Okay, same equation 2 slides ago with an underscore of pi here, and underscore of pi here. So it's the average. So it's the expectation of the immediate reward plus a discount times the value of being in some random state st plus 1. Okay, given that policy pi. Okay, I mean starting from the state s. So it's just like this value function. There's also a recursive equation for this q or action value function as well. It's going to be just the average of the immediate reward plus the q with according to that policy of being in some st plus 1 and taking action at plus 1. Okay, given that you've started from state s and action is. So the only difference is going to be this underlined. I guess this is not there here. Okay, so you're not pre-specifying the action at the current state, otherwise current time, otherwise it's almost the same. Okay, so both have this recursive expressions. Okay, so this recursive expression is actually this recursive expression here itself, okay, this one and this one, these are called Bellman expectation equations. Okay, which is written over there. Bellman was a scientist. He kind of did a lot of contribution towards this sequential decision making and dynamic programming. So this equation, which relates the value at a given state to value at a future state at another state s plus 1, st plus 1, this equality or this equation for a condition on a given policy is called the Bellman expectation equation. Okay, and just like I wrote the explicit, that expectation was hiding a lot of things, so I wrote explicitly what the recursive equation was for just the value function. Here for the action value function or the state action value function, explicitly I'm again writing there's an averaging over the states, next states that you can get to. There's an averaging over all the actions I can take, this part, times the whatever is going to be the action value function from the next state and the next action onwards. So all the things that I can choose for the next state, all the things I can choose for the next action, the action value function for that action. Okay, that times gamma plus the current expected expected reward would give me this recursive equation. That's the gory detail of that E in this. Okay, any questions about this part? Actually, this is okay. Actually, yeah. Okay, so next, so I'm gonna just specify one more thing and then we'll take a break. So we have specified the value function for every state. So given a policy, we can tell you what the value of every state is, and given a policy, I can tell you what's the state action value function for every state and action pair is. Okay, right? I can just compute those expectations if I know the dynamics of the system, which means I know the transition probabilities and the rewards. I can just compute them. Those are numbers, right? Now, the optimal state action value function is a specific bunch of numbers. Okay, so these are numbers. Just think of these as functions, but it's a number for every state. So just think of it as a vector of numbers. Okay, so the optimal such that vector of numbers is those bunch of numbers which are the highest. Okay, which are the highest in the sense of there is a pi. Okay, that maximizes v pi of s for all s. Okay, for every state. Okay, there is a pi which maximizes these numbers. Okay, for every pi there's a different number potentially, and so for every policy there's a different number for that state. So you want to optimize over policies, and that gives you the optimal state value function. Okay, so it's just, I'm just adding the max over pi in the front. Okay, because pi is something that I fixed before, and for every fixed thing there was there's a recursive equation that we saw, but there's a number for every state, v pi of s for every state. Right, now I'm saying, okay, now I want to change the pi and get to that pi which maximizes these numbers. Okay, same thing where here I just added a max and I call it v star and q star. and these guys satisfy what is called the Bellman optimality equation. Okay, by which I just mean, okay, I didn't write the optimality equation. Oh no, I did write the optimality equation. So here I'm just writing the optimality equation for Q. Okay, Q star. So Q star. So previously, Q pi of s comma a was just r plus gamma times the summation, and there was again a summation over actions of the particular policy times q pi of s prime a prime. Okay, now we have a max operation. Okay, so that's why this is a slightly different equation called the Bellman optimality equation. Okay, we are not deriving this. I mean, this can be derived, but for us, we just want to know that there is a recursive equation even for the best action value function is the best action value function. Basically, there's a recursive equation for even the best action value function, not just a recursive equation for an action value function given a particular policy. Okay, so there are two different equations. One is called expectation equation. One is called the optimality equation. Okay, and the optimality equation is almost the same form except for this max of a prime here instead of summation over a policy, because there's no fixed policy. I mean, there's no explicit policy here that we have written here. Okay, so that's the Bellman optimality equation, and if you know the optimal state value function, then the optimal policy is just the argmax of over all actions of that value function. That's kind of obvious, right? So recall that I'm finding so q star of s comma a is the best q value that I can assign to that state and action pair over all policies. Okay, and remember q star of s comma a is the expected reward that I can get from that time onwards, some sum of rewards. And so the best action to take is essentially whichever action will give you the best total sum of rewards. So you had this second variable which you get to choose. So you can just choose action to be 1, 2 or 3 depending on whether you plug in 1 and you get a higher number, plug in 2 or you get a higher number, plug in 3 you get a higher number. Okay, so that's all. So that's the policy. And in this case, so in this example, I guess I didn't specify the exact setting, but in this example I'm saying that the optimal policy is deterministic. Okay, so if you have a infinite horizon, basically remember I did an infinite sum over rewards, and I said because of discounting it's a finite quantity. In that case, your optimal policy is deterministic. Okay, which means that you only take one action and all other actions you don't care about. I mean, it's a deterministic policy. It's not a stochastic policy. Okay, so that's the optimal policy, and once you know the optimal policy, you can keep executing that to maximize your reward. So if you know everything about the environment, if you know the P matrix and the R function, and if you can find Q star somehow, then you can just use Q star, you get pi star, and you can just apply pi star and you get as much reward as possible in expectation, and you're done. Okay, that's without the learning problem. Okay, there's no learning here. I mean, you figure out what's the best policy is and you can just apply it. That's a computational problem here. Any questions up to this part? Okay, let's take a break for 13 minutes. 13